Alrighty, I think we're up and running. This is lesson set 15. I don't know what that box is doing there. It's off now. And I'd like to start most of these lesson sets now with just a little bit of conceptual chatter. Let's talk a little bit about some of the concepts, the major concepts that you want to pick up at this level. And I like to do that in a repetitive way. So I brought the magic box, and I'm just looking at volume. So let's think of x as one dimension. This is a three-dimensional shape, x times x times x, perfect cube. Okay, and here's some numbers that go with it. 0 cubed is 0, and 0.0001, 4 decimal places, gets me 12 decimal places with a 1 at the end. Whereas if I cube 2, I get 8, and if I cube 2.0001, I get 8.0012, 0006, 0001. Some significant change. And I think it's reflected in, at 0, it's flat. There's no change. There's nothing changing there. Pretty hard to get a lot of change when there's no box. Yeah. Whereas at 2, I have 8 units of volume, and I'm going up at 12 to 1. And I think we can see how these numbers work. The change in y, which is volume, from 2 by 2 by 2 by 2, if I put a layer of change on it, I've just added to the volume. And if you look at it, I see 3 squares with a little bit of thickness. And I'm using 0.01 as a standard consideration of thickness. And every time I add a little volume, then the next layer is just a little bit bigger in this case. A little bit bigger. And if I keep adding layer after layer after layer, 10, 100, 1,000, 10,000, if I put 10,000 changes, 10,000 Riemann sums, I'm going to get a change of 8 to 3 by 3 by 3, 27. I'm going to get 19 units of volume added to the box as I keep putting layer after. That's integration. And so that's a repetitive conversation. It's not the first time you've heard that, but the first time you heard something, it may not process. Second time, maybe a little bit better. Third and fourth time, maybe it comes into focus. If not, maybe it's a radian measurement. You still don't know what a radian is. Maybe you got to hear it 100 times. So if that's what it takes, that's what has to happen. And the only way I think that can happen is to put a lot of problems in front of you and just talk about them briefly each and every day, for as much as possible. All right, so I think another name for calculus is, as far as I'm concerned, the layering machine. All right, looks like I've got a little battery problem, so I hope this is still working and you can see things. And now we're going to do the lesson set 15 pretty quickly. So I stop rambling. Average rate of change of x cubed plus 2x from -1 to 2 is just the slope from -1 to 2. -1 to 2 for x cubed plus 2x. -1 minus 3, 8 and 4, 12. So it looks like I've got from 12 to -3, 15 units of change, and it took a change of 3 for the x's. So it's 5 to 1. So this is going up through the origin at 2 to 1. And somewhere, -1 is somewhere there, 2 is somewhere here, and I'm going up at 5 to 1. There has to be at least one place in the interval. This function has 2 places where I go up at 5 to 1. One of them is over here, parallel slope, and another one looks to be near, and I don't know exactly where over here, but well, let's find out. Let's do the derivative, 3x squared plus 2, and let's set it to 5 to 1. Let's find those places where we're going up at 5 to 1. Oh, I can see it, plus and minus 1. Now that's a problem for me, -1. Do I accept that answer or not? It says the closed interval, so I'll leave that for the math majors in college. For our purposes, let's just move on. But this one over here is +1. And that's what C represents. I think they use C because the change from A to B has been taken. Those letters have been taken, so we'll use C. All right. Next problem. That's 2 down, and this is about 22 problems, I think. Front board, side board, back board. Sine function, 5 pi over 3. You should be able to tell me the sine of 5 pi over 3, negative root 3 over 2. 1/2. Should be able to construct those quickly and easily. There's your 90-degree triangle, and there's your 60-degree reference angle. 5 pi over 3 is a radian measurement. It's roughly 5 of these lengths. Take you to here. Okay. All right. Usually people struggle with the algebra and the trig more than the calc, so I am layering a little discussion about the unit circle. So if you can't do this, it's going to be hard to do these problems. So go back to the algebra to trig lesson sets, look in the playlist for the trig lesson set, look at the introduction to the unit circle, and what is a radian, and put away the calculus for a while and make sure you have that skill in your pocket. All right, so the derivative of the sine is the cosine. So what's the cosine? 1/2. X minus 5 pi over 3 minus root 3 over 2 is the tangent, which would be right about there, on 1 period of the sine function. All right, moving right along. We want to do 4 rectangles, right-hand rectangles, and 4 trapezoids for y equals e to the x from -1 to 2. So -1 to 2. Here's -1. Here's 2. That's 3 units. I need 4 rectangles. So I've got to do that. So that is 3/4, 3/4, 3/4, 3/4, 12/4, 3 units of change. This is -4 over 4. So if I add 3/4, I'm at -1/4. If I add 3/4, I'm at 2/4. If I add 3/4, I'm at 5/4. And if I add 3/4, I'm at 8/4. So I've got that down properly. Now, there's e to the x. I want right-hand rectangle, which is going to be an over approximation. And this is e to the -1/4, which is the same thing as 1 over e to the 4th. This one over here is going to be e to the 1/2. I don't like that. Oh, fourths, half, 2/4. Okay. E to the 5/4. I feel like I'm making a mistake here. And e to the 8/4, or e to the 2. All right, so cut to the chase. Widths are 3/4. My first rectangle is based on e to the -1/4. I don't know. I think I botched that. So let's call it that. Let's just call it that. That's where I think I had a little trouble. The next one is e to the 1/2. Then we have e to the 5/4. And e squared. E squared is a little bit bigger than 7. I'll put a bracket there, okay, just to highlight it. And that's our 4 right-hand rectangles. Okay, and now we have trapezoid. Trapezoid is going to use the interior ones twice and the outside ones. So I got 3 interior, 2 outside. So width divided by 2 becomes 3/8. I only used this one once, and that's e to the -1. This one is doubled because I'm sharing it. Those 2 trapezoids share this one, so all the interior ones are doubled. And the last one is 1/2, so 1, 4. Trapezoid should have 5 things inside. I only have 1, 2, 3, 4, so I forgot to add this one over here. That was a double as well. So e to the -1, 2e to the -1/4, 2e to the 1/2. There, I'm finally getting there. 2e to the 5/4, and the last one is a singleton, e squared. There, that's better. Let's get rid of that. Okay, at least it's done properly. You're pausing the video and having a go at each of these problems. All right, basic integration now. Can you do 1 to 16, the integral 1 to 16 of 1 over x to the -1/4? I think that's why I was having some trouble here, because that's a little Freudian issue here. All right, so 1 over x to the -1/4, hopefully you know, is the same as x to the 1/4. So if I'm going to integrate x to the 1/4, I have to add 1 and then divide by it. Taking your time with that gets you x to the 5/4 divided by 5/4 is multiplied by 4/5. We're going to do the fundamental theorem from 1 to 16. So I'm going to drop 16 in. Fourth root of 16 is 2. 32, 128 over 5. Drop a 1 in, we're going to get 4/5. Yep. Answer, 124 over 5. Given x to the 2/3, find y prime. Remember, we've only been at calculus for 15 lesson sets now. That's 3 weeks in a classroom. So if y equals x to the 2/3, then y prime is 2/3 x to the minus 1/3. We're going to do 2/3 minus 1 for the exponent, which is minus 3 over 3. All right, so you multiply, drop it down one, polynomial. Power rule. All right, limit as x goes to 8. Oh, did I even write the problem down? No. So, okay, that's what I want you to do. I want you to figure out the derivative of x to the 5th, x cubed, as x goes to 8. I don't even want to say as x goes to 8. I just want you to show me with a limit why y prime is 3x squared. Show me with a limit what's going on there. Two ways. Two ways. Well, one way, x, and I think instead of x going to 8, I think I want to go to 2. All right, so I should have written more down there to remind me what I was asking. So we have x cubed, and we have 2, and we have 8. All right, so my apologies, because if you're pausing the video, I'm doing a whole different problem now. My apologies. So one of the ways to see this is the limit as x goes to 2 of x cubed minus 8 over x minus 2. We actually did that at the start of the class, right? We did 2, 8. I'll do 3 decimal places this time to shorten it up. 012, 006, 001. And what is this number doing? What's that number doing? It's getting close to 2 from the right. Okay, I'm looking at it from the right-hand side. Okay, and I can see that I'm really replicating with this the derivative of that. That's what it's about. Now, this, of course, if you factored this out, if you put this in factored form, x minus 2 times x squared plus 2x plus 4, right? Factoring the difference of 2 cubes, we can see the x minus 2's canceling. Now I can put 2 in, and if I do, I get 4 plus 4 plus 4. 3 squares. That's what we did at the beginning. All right, so hopefully you're making some connections. Now, another connection that I hope you can make is that from 7 to 2 is a horizontal change. Well, so is this. 2.001 to 2, that's a horizontal change. What is my horizontal change? My horizontal change in this case is 0.001. Well, what's that going towards? What? I hope you see it's going to 0. So you could have written the limit as h goes to 0 of. Now we have to nail this thing. So we have to have 2 plus h cubed minus 2 cubed, which is 8, all over. This becomes x plus h, or 2 plus h. It becomes 2 plus h, and that h is going to 0. And that this one becomes 2 plus h cubed. Now what is that minus that? Well, the 2's cancel and you get h. All right, so there's a couple of ways that we try to express this process. All right, so let's get rid of this because that got in my way. Let's get rid of this now. We're getting there. What's the limit as x goes to infinity of x to the 4th, 4 to the x? Well, you play with this. You put some numbers in like, I don't know, put 10 in and do 4 times 4 times 4 times 4 10 times, and then do 10 to the 4th and compare. And then think about 100 times. 4 times 4 times 4 times 4, 100 times. This is exponential growth. That is always going to outpace polynomial growth. X to the 4th is going up like that, and an exponential function eventually starts going up almost vertically. As I go to infinity, a small change in x, huge change in y. So this thing is going to go to 0. You have to think about it, plug some numbers in. If you have to put it in a grapher, put it in a grapher. Whatever you have to do, you do in order to understand that. I'm putting the onus on you that time. All right, local min for this cubic. Okay, so we've got to get p prime of x, which in this case is multiplied by 3, 3's cancel, minus 2x squared, plus 8x, minus 2. We also need to know where the concavity changes, so we're going to do double prime, which is minus 4x plus 8. Minus 4x plus 8 cuts through at x equals 2, changes from negative to positive, and we're looking for local min. So local min. So when does this equal 0? When x equals 2. So we have something that's concave down. Concave up and then concave down. So this cubic is concave up and then concave down. Something like that. So our local min, local min is on the left, right, where it's concave up. All right, so we're going to find out where our slopes are 0, so we got to set this thing equal to 0. We want to look at when that happens, and if we divide by 2, we got to do some algebra here. Minus x squared plus 4x minus 1 equals 0, so I'll bring that to the other side and make it x squared minus 4x plus 1 equals 0. This was unfortunately a little trickier than I had wanted to do. So if I move that to this side, I complete the square, so I got x minus 2 squared minus 4 equals negative 1. So therefore I've got, this becomes positive 5. And then I get plus minus, so I have 2 plus minus the square root of 5, I believe. And so this one here should be at x being 2 minus the square root of 5. Now I went after that pretty quickly, and I should have given you some friendlier numbers here at this stage of the game. And I could have butchered that somewhere along the way, but that's the process. Okay, you got to prove that it's a local min, and the concavity, concave up, can do that, provided the slopes are 0 at that instant. All right, so much for that. I didn't pick a very good problem for this stage of the term for you to do. I should have had, as I said, some integer-friendly numbers, easier to talk about. But if I got lost in some of the computation there, let it pass. Now, I just erased everything. I hope that was the last problem on this side. It is now. All right, so our third time taking a crack at a problem like this and answering all these questions, which I hope a month from now, you could just go boom, 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 and within a minute answer all of them. All right, so what do I see here? Well, I can see f of x is the area accumulating from 1 to x under this g function. So I'm really measuring from here. And if I go in that direction, I want to know when f of x is increasing. Well, I need the derivative. Oh yeah, there's a way to get the derivative quickly, right? If I did this integration, I'd have big G of x minus big G of 1. And if I took that derivative, I'd have little g of x. Right? So if I drop it in, I get g of x. If I multiply by the derivative of this, I get times 1. If I drop it in, minus g of 1. And if I multiply that by its derivative, I'm multiplying by 0, so that disappears. So I've made the connection that this is a picture of the derivative of f. That's good enough for now. And so what am I increasing? When this fella's derivative is positive. Well, look at this whole interval is positive except at the endpoints in -2. Looks like I'll take always going up. At this stage of the game, you can say always going up. Instead of -4 to 2 union, -2 to 4, I'll take always. I don't care. We just talked about what f prime of x is. It's g of x. We just did it. Okay, what is f of x? F of x, I suppose, is g, big G of x minus big G of 1. So we talked about that a little bit. What is f of 1? F of 1 is the area accumulating from 1 to 1. So how much can I draw from 1 to 1? I don't think I can draw anything. When is f of x concave up? When its derivative is what? Its first derivative. How do you do concavity for first derivative? Are you increasing or decreasing? Is the derivative increasing? If the derivative is increasing, then that next slope is bigger than the previous one. If the next slope is less steep, then what's happening? My slopes are going down. My slopes are going up. Here are representation of your slope values. I'm going up. Here's another place I'm going up. I'm going down. I'm not changing at all. I'm going down. So when am I concave up? From -4 to -2. Union, -2 to 0. Takes a while for you to see these things. But we just keep talking about them until you do. We don't leave these conversations, and if you don't get it by the end of a semester, well, I'm sorry, we tried. So what's f of -4? Let's do f double prime, let's do f of 4 first. Let's do f of 4, it'll be easier to see that. F of 4 is the area from 1 to 4. Well, that's a rectangle and a triangle. All right, so this is a width of 1 and a height of 2. This is a width of 2 and a height of 2. So that's going to be 2 units of area, and so is this. All right, so what is f of 4? F of 4 is 4. 4 units of accumulation. If I'm looking to the right and things are going up, then when I look to the left, they got to be going down. So from -1 to 2 is 3 units of width, and I still have a height, a rectangle. I got to do the rectangle. 1 times 2 is 2, but in this case it's -2. And now I'm doing 2 units of width, height, so this is also -2. Oh yeah, I got the symmetric picture. I didn't spot that initially, talking to you. So right now I'm at -4, and this is a units, 2 units, 2 units. So this is also down 2. 2 units. Yeah, I guess so. So looks like -6. So f of -4 is -6, unless I made a mistake. Now what is f double prime of 2? Well, f double prime of 2 is the rate of change of f prime. And how do I do that? That's called a cusp. Right? That's like an absolute value. I'm always going down to 2 to 1, then I'm going up at 2 to 1. So what the heck is happening there? I don't know. I don't know how you go from the number -2 to 2 without a transition. And it doesn't appear to be one. So we say that's undefined. Whereas, let's just stop there. I'm just going to stop there because this video is getting lengthy. Now you see if you can do the integral of x over e to the, what did I ask here? Oh, that's e to the x over 4, excuse me. So can you integrate e to the x over 4 dx? Can you just write your answer at this stage? I hope that some of you might be able to. If not, then you do your u substitution and see if you can make the connection that the chain rule says that I should have a multiplication by 1/4. If I don't have a multiplication by 1/4, maybe I'm multiplying by 4. Let's find out. U equals 1/4 times x. That's another way of saying x over 4. Division by 4 on the left. So now du is equal to 1/4 dx. Dividing by 4 on the left is multiplication by 4 on the right. And so now I have e to the u and du, and this is this is 4 dx over here. That's all I have. So that 4 can come outside. And it looks like it's 4e to the u. Let's substitute u right now. X over 4 plus c. Yeah, I didn't see multiplication by 1/4. guess we got rid of it. Maybe that's getting a little easier to see. Number 18. I haven't done one of those in a while. Can you take that derivative? I'll do it over here and see if you get the same answer. The first thing I have is taking care of the fourth power, which is a 4x cubed derivative with respect to where I am on a curve, which is determined by the cosine of 2x. Oh boy, didn't leave much room here, so I'll do it here. 4 cosine 3 2x. Then I have to do the derivative of cosine, which is minus sine with respect to where I am on the curve, which is determined by 2x, times 2. All right? And you can leave it like that. All right, can you do number 19? See if I can. I like practicing that. My answer is going to be minus 15x squared minus 3x squared y squared becomes positive 3x squared y squared all over minus 2x cubed y. Hopefully I'm getting better at this, plus 15y squared. All right, so let's do it out. Let's do it out over here. Remember, anything to do with dividing by dx, this is going to have a dx layer of change, right? dy is equal to 15x squared dx, bringing it back to where we started the lesson set here, had that discussion, right? And so if I want dy dx, I divide both sides by dx, well, that's going to disappear. Whereas if I have y squared, I've got to change in y in order to analyze that. I'm going to end up with a dy. If I had something like that, I'm going to end up with the derivative. All right, so cut to the chase. 15x squared minus 3x squared dx times y squared minus, bring the 2 in front, 2x cubed y dy plus, see, I'm running out of room here. Right, so I'm going to take the shortcut and just write the following. 15x squared minus 3x squared y squared minus 2x cubed y prime plus 15y squared y prime equals 0. Okay, so what's going to happen with 15x squared? Goes the other side. What's going to happen with minus 3x squared y squared? Goes to the other side. What's going to happen with this multiplication? It's going to come over here as a division. And what's going to happen with this multiplication? Going to come over here as a division. And now if I want to know how this thing is changing in an instant, I need an x and a y value. I need a coordinate. All right. That's 23. I erased that. Getting there. We're getting there. I write this as an integral expression. Can you write this function as an integral? This may be the first time I've ever asked you this question. I've talked about it, or I wouldn't have phrased it. I wouldn't have put it on here at all. So, how do you get these statements? They come from the area under its derivative. Okay, so what's the area under the derivative? Well, we get the derivative, which is 6x squared minus 5. Okay, dx. And now we got to get some numbers in here. Well, I can see that a 0 gets me 7. I can also see that a 1, 2 minus 3 plus 7 gets me 4. Why don't I use a 1 gets me 4? From 1 to x plus 4. Remember what we said from 1 to 1? How much area accumulates? Nothing. And I get 4. Now, if we drew this out, I think I'd rather do a linear one with you first, because then you got geometry to help you see the area accumulation. All right, so that's that. So if you do this out, you would have gotten that polynomial. So we've got to integrate acceleration to get velocity, so 2t. So velocity becomes, don't get the ink all over the place, dt becomes t squared plus sine t plus c. Hopefully I picked an easy number. Yeah, the sine of 0 is 0. So if I want 3, I guess I got to have c 0 gets me 3. So 0 gets me 3. So I got to solve this for 3 plus or minus root 3. Interesting. Not quite sure where I'm at in this. Oh, cosine acceleration. See, 0, cosine of 0 is 1. So I probably wanted to do that. And yet I didn't. So I'm going to change this problem so that I can do that. So let's make this the sine t, which makes this the cosine t. Poetic license. Okay, I'm over 70. I get to do things like this. When you get to be my age, you get to change things like that. And I am. All right, now when I put a 0 in, I get 1. And I want 3, so now that becomes a 2. Boy, that helped me out a lot, because I don't feel like figuring out what I just got myself into for a conundrum. All right. Do you recognize it? Oh, do you recognize it? I hope so. I hope you say that this is 80. I hope you see that I'm looking at 2 getting me 32. And 2.01 getting me 2.01 to the 5th. And I don't know what that is. But when I subtract these, I'm getting a very small change in x. And when I subtract these, I'm getting a concomitant change in y. Might be positive, might be negative, I don't know. But I'm replicating the derivative process for that function. And the derivative of that is 5x to the 4. And if I drop in a 2, I get 5 times 16. And I saw all that. Now, let's actually do this out algebraically. That's a good question to ask you, isn't it? That's one of the reasons we spent so much time in my class figuring out how to do this on the fly. X minus 2 times what gets me x to the 5th minus 32. Right? It's a division. So I need x to the 4th. Now I have minus 2x to the 4th. I don't see any x to the 4th. So I got to create 2x to the 4th here. And so I got to multiply this by 2x cubed. Because that gives me 2x to the 4th minus 2x to the 4th, and I don't see it. So now I got to ask, well, where the heck am I? Okay, I am getting 0. So right now I have minus 4x cubed. I don't see any x cubes up there. Does anybody see any x cubes up there? I don't. So I need positive 4x cubed. So I better do plus 4x squared. And that gets me 4x cubed. Oh, that disappears. But unfortunately, it gets me minus 8x squared, and I don't see any x squares up there. So I got to get that minus 8x squared. I got to get rid of that. And I got to multiply this by something. Why don't I multiply it by minus 8x? And what is minus 8x times minus 2? Well, that's 16x. I got to get rid of that. So I better multiply by minus 16. But I'm going to put it out here. So that's another name for our function right here. That's the same polynomial here, right there. That's that thing divided by x minus 2. Let's put a 2 in this because I don't think it's undefined. I get 16. I get another 16. I get another 16. I get minus 16. Did I make a sign error? I think I made a sign error. Minus 16, 16, 16. Oh, God, right at the end here, and I made some kind of sign error somewhere. Oh, but I'm over 70. All right, so if you could take more time with it, you might want to do the old-fashioned x minus 2, x to the 5th, x to the 5th plus 0x to the 4th plus 0x cubed plus 0x squared plus 0x minus 32. Go ahead and do it out. You plug 2 in, plug it into your answer. You're going to get 80. All right. I can see I did something stupid here. I should go back and find it, but I got to be someplace, so I'll let you find it. Quotient rule, low. All we're trying to do is find y prime for that. Low. D high, the derivative of 2e to the 4x is itself times 4. Chain rule. Minus high, 2e to the 4x times the derivative of low times 3x squared all over low, which is x to the 6th. Average value for the sine function over the interval 3 to 5, sine x plus 10. So I just wanted to get you something up here, right? And so what is the calculation? It's the area under the curve from 3 to 5, it's that area, divided by the width. So, just the calculation, because I want to get out of here. Sine of x plus 10 dx, there's the area under the curve from 3 to 5, and 5 minus 3 is the mechanics for finding the average value of the function. And one more time, x squared, the right-hand part of x squared, if I wanted to go from, say, 0 to 10, then I've got this area, I reshape it into a rectangle, where that area gets offset by that area, and that altitude right there, is the average value of the function y equals x squared from 0 to 10. All right, so we got some practice, a couple of rough places in there. You know me, I run into trouble, I'm an old guy. All right, so hope you're getting some practice. We'll do the second half of that test tomorrow.